Today we'll be implementing Sequence Detector 101 using VHDL code. So let's jump right in. First, create a new project. Give some name that I'm going to be implementing the Sequence Detector using Murray state machine in this video. So I'll be giving Murray and then Murray Seq detect, let's say. So that's what we are going to be doing now. Murray Seq detect. Please check if it is in schematic top level source type and click on next. Check if this is in VHDL because I'm going to do it in VHDL and then click on next, finish. So we have created our project. Now click on it, right click on it and then click new source and then give a name for the file we are going to create. Since I'm going to do test bench first, I'm going to give it as test bench Murray and then I'm going to use VHDL module and then next, finish. So I can remove this is not necessary and I'll increase the size. Okay, so now we are ready to jump into the Murray sequence detector using VHDL code. So at first what we are going to do, so I'm going to give a comment. So test bench for Murray sequence sequence detector 101 using Murray state machine. So let's look at the implementation now. So the first thing which you have to do is you have to add a library which is called IEEE. So library IEEE. This library contains it is a very very widely used library in VHDL. It contains a lot of standard packages, including the next package we will be using standard logic 1164, which is very useful for representing digital or binary values. So now we have to use standard logic 1164.all. So this package is really useful for implementing digital values and also provides operations which we can do with those values. So yeah, now we have to declare an entity. An entity is entity. An entity is something which is used to describe an interface of whatever we are designing. In this case, we are designing a sequence detector unit. So an entity is used to describe the interface of that. So entity, we are going to give a name to the entity. Let's say TB Murray, test bench Murray, and then is, and I'm going to end the entity. So what I've done here is that I have declared a test bench entity TB Murray, and it is a test bench entity which is used for simulation, whatever simulation we are going to create in the upcoming uh, upcoming code. And I'm also testing the values, giving a lot of values. So a design for the design unit, I'm going to describe the design unit using an entity. And the next thing what I have to do is, okay, I have now created an entity, but now I have to give an architecture to that entity, right? So I have to provide the structural, the behaviors, and also the what and all entity is going to implement, right? So that's why I'm going to declare an architecture, and I'm going to name that architecture behavior. architecture behavior of DB Murray is, and then what I'm going to do is I'm going to declare a component declaration. The reason why we are declaring a component is that we want a component. It is a block of code. A component is a block of code which describes the interface of the entity. So the entity describes the interface of what sequence detector we are creating, and the component describes the interface for the entity. So we are going to name the component More, and then what we are going to do is that I'm going to define the ports. For a component there will be ports, but remember, for an entity there won't be any ports for test bench, but for components in a test bench there will be ports. So I'm going to name this port, and then I'm going to give four ports, 3 input and 4 output ports. And the first port is clock port, clock, and then I'm going to give this as an input port, clock's standard logic. So this denotes that it is a clock port or signal, and this is a clock port or signal. And then I'm going to give another input signal called DIN and say it is an input port, and I'm going to say it as standard logic. So this is called the data input, whatever we are inputting, and then we are going to give another input port and say in standard logic, and this is called the reset port or signal. And then what I'm going to do is I'm going to give an output port which is called dout and say out standard logic. And the what this represents is that it is data output. So I'm going to close the port now, it's not necessary, and I'm going to end the component. I'm going to end the component here. So I've declared an architecture and I've given the components. I've declared a component named Mure, and I've declared the ports for the components, and I've ended the components. Now what I have to do is I have to give input signals, right? These are all ports, right? Clock port, D in port, reset port, D out port. The next thing is I have to do is I have to give inputs signals which are going to be matched in the input ports, and the output signals are going to be matched in the output ports. And one more thing, the clock signal, clock, D in, reset, these are all the type standard logic. All right, these ports are of the type standard logic. All right, and the next thing is in the input ports we have signal, clock, and we are going to initialize the clock to a standard. This is of the type standard logic again, and then what we are going to do is I'm going to initialize the clock signal with 0. Similarly, I'm going to initialize the DIN signal with 0, and I'm going to initialize it with 0, okay, again, and I'm going to initialize signal reset to 0 again, and then I'm going. These are the input signals: clock signal, DIN signal, reset signal. These are input signals. Now I have to give outputs, right? Now output signals. Now in the output signals, I'm going to have only one signal, sorry, signal D out, and then I'm going to give standard logic, and then equals. I'm not going to give any initialization for this because this is the output signal and the value is going to be represented in this. So next I'm going to give something called clock process definitions. The reason why we are giving this clock process definitions is that we want to observe the clock signal more clearly, right? We don't want it to be, continuous and stuff like that. So we are going to give a constant clock period signal, which is the constant time period for the clock signal, and we are going to initialize it to some value. And remember, this clock period, what I'm going to define now, is of the type time, which is present in the standard logic package. So what I'm going to do is I'm going to define a clock period, sorry, not clock process, it's a clock period definition. So clock period definitions, what I'm going to do is I'm going to give a constant clock period, indicating that I'm going to give a time period for a constant time period for a clock signal, and this is of the type time, so I have to give time equals time equals, let's say, 50 nanoseconds. So what I've done here is I've declared a clock period, which is a time period which is of the type time, and I've initialized to 50 nanoseconds, and this is the constant clock period. So next thing is I have to implement the main body of the code, which is begin, and then what I have to do is I have to um, construct, right? I have to construct the create the sequence detector, right? So sequence detector, right? So and then what we are going to do is I'm going to give a name or a label to the sequence detector we are designing, and I'm going to give a name called UUT, and I'm going to use the component Mure, and then I'm going to map the ports and the signals. That is what we are going to do in um, the creating the sequence detector. So basically we have an input signal and an input port. We are going to map the input signals and input ports together. Similarly, output signal with output port. So if you want to do this, so I have to map the clock port with the clock signal. I have to map the D-in port with the D-in signal. I have to map the reset port with the reset signal. I have to map the D-out port, which is the output port, with the D-out signal. Now I'm going to end this. So what I've done is I've mapped all the input ports and the output ports with the respective input signals and the output signals. So the next thing what we have to do is we have to create a clock process. So a clock process is something which is used to model concurrent behavior. We are uh, so in clock process we are having a specific model behavior, and in the next thing is that we are going to begin. Then in the next begin we are going to initialize the clock to, and then we are going to initialize the clock to 0, and then we are going to wait for some particular time for and that time is given by the clock period divided by 2. And the reason why we are doing this is because this represents the first half of the clock cycle. And then I'm going to initialize the clock with 1, and then I'm going to wait for again the clock period, the same half, the second half, the clock period. And then what I'm going to do is what I've done till now is that I have started the definition process, clock process. It is a process to model some certain behavior, a model concurrent behavior, and I am going to begin the clock process. So I've written begin, and I have initialized the clock signal to a logic low level, and then I have paused the clock signal for the first clock period, one half of the clock cycle, and then I have set it to 1, and I have set the clock signal to 1, and I have also given another clock period wait denoting the second half of this cycle. And then now I'm going to give the end process. I'm going to end this clock process now. Okay, we have now mapped the input and output ports together, and I've also given clock process. Now we have to generate the input values, right? Input value generation, and this is also called as stimulus process. So I'm going to name the process stim proc again. I'm going to name it stim proc, and then what I'm going to do is I'm going to begin the input generation process, and then I'm going to first initialize with 0. I'm going to initialize with 0 and then wait for, let's say, 100 nanoseconds, and now I'm going to initialize the clock to 1, and then I'm going to for wait for, let's say, again 150 nanoseconds, let's say. And after you give clock is equal to 1, you have to implement one more thing. You have to write dn, the dn signal equals 0. You have to give this, you are going to set the din input with logic low level, and after that you're going to set the dout logic, the dout to Alright, so we are done with the clock process definitions. So now what we are going to do is that we are going to generate the input values, right? So we have to generate the input values which are going to be used as inputs. So this process is also called as stimulus process. And in the stimulus process, I'm going to name this process as stimproc, and I'm going to name this as stimproc, and then I'm going to begin the process, and then what I'm going to do is that I'm going to set the reset to a value of high, logic high, and then I'm going to wait for 100 nanoseconds. And then what I'm going to do is that I'm going to set the reset to 0, and then I'm going to set the din to din to 0, and then I'm going to wait for 100 nanoseconds again, and then I'm going to set the din to 1, and then I'm going to wait for, let's say, 50 nanoseconds this time, and What I'm going to do next is that I'm going to set the D in again to 0, and then I'm going to wait for 30 nanoseconds, and I'm going to set the D in to logic I, and then I will wait for 40 nanoseconds, and then I will again set the D in equals to a logic low, and then I will wait for 150 nanoseconds this time, let's say. And now I'm going to set D in to logic high, and then wait for 60 nanoseconds. So I've given these kind of things. So once you give sufficient amount of D in and D outs, you can end the process, and then you can end. So this is the test bench code uh, for the sequence detector using Murray state machine. So basically, what I've done here is that I'm setting the reset to a logic high first, and then I'm going to wait for some time, and then I'm going to set the reset signal to 0, and then I'm going to set the D input signal to a logic low level 0, and then I'm going to pause the execution for some value of time, and then I'm going to set it to 1 and then pause the execution, and then I'm going to set to 0 and pause the execution. So similarly I'm doing it for repeat some patterns of times. The same pattern you have to repeat for some amount of time, and then finally you're going to end the process, and then you will end the program. So this is the test bench code for Murray state machine sequence detector 101. So let's check this code. Yeah, it's working. So yeah, it's working now. And now I'm gonna simulate the process. I'm gonna check this, and I'm gonna check behavioral syntax check. Yeah, it's done. So now I'm gonna simulate the behavioral model. So yeah, our test bench simulation is given here. So everything is working perfectly now. So you can close this. And now what you have to do, you have to implement the actual sequence detector 101 code using Murray state machine onto this test bench Murray code which you have written. So what you're going to do is click on this and right click and um, press new source, and then you're going to type actual Murray, and then what you're going to do is click on VHDL module and click next, finish. So yeah, we have created another source. Now what I'm going to do is I'm going to remove this, we don't need this. Now I'm going to increase the size. So we had implemented the test bench code for the Murray state machine state detector. So now I'm going to implement the um, actual VHDL code for the sequence detector 101 using Murray state machine. So actual sequence detector for Murray state machine 101. Now I'll write some blocks of code, then I will explain what is going on here. So So yeah, what I've done in the above blocks of code is that I have included a library called IEEE, and then I have included the standard package, standard logic 1164, which contains the binary values and also the operations which are performed for the binary values. And in the next line, I have declared an entity named Mure, and an entity is, as I've said, is the description of an interface which we are designing in digital systems. It has input ports and output ports. So I have declared the input ports clock, DIN and reset, and they are of the type standard logic. And I have declared DOUT, which is an output port which is type standard logic, and I have entered the entity endmore. So now what I'm going to do is I'm going to define the architecture of the uh, I'm going to define the architecture of Mure, right? So I'm going to name this architecture as behavioral of Mure S, and I am going to give some states: next state, current state. These are the signals for the Mure sequence detector. So I'm going to give type state is, so these are the four states which I'm going to give. The reason is we have to we have to represent different states in the Murray state machine, right? So that's why we are creating all possible values, which are the four all possible values. We are creating it to represent the different states in a state machine. So the next thing is I have to declare the signals which are used here. So we are going to use present state signal and the next state signal. Next state signal. The next is I'm going to use I'm going to have to implement this from state. So signal, present state, next state, and then I'm going to begin a process called synchronous process, and synchronous process, I'm going to name this process as synchronous process, and then I'm going to begin the process. And then basically what I'm doing in the synchronous process is that this process is sensitive to the clock signal. This synchronous process is sensitive to the clock signal, so I'm including clock in this process, and this will execute only when there's a change in the rising edge of the clock. So in the next statement, I will be checking if there is a rising edge of the clock signal. The following statements after the checking is executed only when the rising clock edge is detected. So I'm going to tell if rising edge of clock is detected. If rising edge of clock, then if reset value equals logic high, then present state is set to 0, is set to initial state, sorry, is present state is set to state 0. Yeah, so set the present state to 0, and then after you are done doing this, else present state is set to, if in the absence of a reset, if there is no reset, then the present state is updated to the next state. Present state is updated to the next state. and then we are going to end if, and then another end if, and then we are going to end the synchronous process. So what I've done is that I've declared a process called synchronous process, and I've begun it. And if we detect a rising edge in the clock, then if there is a reset present in it, then present state should be set to the state 0, or the initial state. This is the initial state, state 0. ST0 is the initial state. If there is a reset, set the present state to initial state, else set the present state to the next state. So end if, end process. So that is going on here. And the next thing is I'm going to implement an output decoder, and the output decoder is sensitive to changes in the present state and the DIN. So output decoder is a process of present state. It is sensitive to DIN and the present state. The output decoder is sensitive. So we have to begin, and we have to set the next state as the initial state, and then we have to have a case. The case is a statement which checks the current state, present state, which is the present state, and defines the logic for updating the next state based on the combination of the current state which we are using and the input DIN which we are using. So inside each when block which we are going to be using, case when, so inside each when block we are going to implement a logic for updating next state based on the current state and the input condition. So here the case block, in the case block, case present state is when st0 so what I've done here is this: the statement checks if the current state, which is the present state, and defines the logic for updating the next state based on the combination of the current state and the input DIN. So uh, if DIN equals 1 is an output high, if DIN equals 1, then we should set next state as the st1, and then else next state should be set as the initial state. End if, and I'm going to end the end if, and when st1 is, so when st0 I have to implement these conditions, if else, and when st1 I have to implement these set of conditions. DIN should be, if DIN is 1, then next state should be set to state 1, else next state should be set to st2. Again I'm gonna end if, again when st2, then I have to give if dn equals 1, then then next state should be st3, and then else next state should be state 0, and if when state 3, if dn equals 1, then next state should be set to state 1, and then else next state should be set to state 2, when others should be next state set to state 0, end case, and end the process. So basically what I've done from this output decoder is that I've declared an output decoder process which is sensitive to changes in the present state and the D input state, and we are going to initialize the next state to initial state, and the case when this statement is a statement which checks the current state, this is the present state, and defines the logic for updating the next state based on the combination of the current state and the D input stage. Present state is when, yeah. So for different state, when state 0, when state 1, when state 2, state 3, if dn equals 1, we are current exactly updating the next state to the next state, and if else, then we are backtracking, and then we are going to define another process called next state decoder, and in that this is also a process, and in this process is dependent upon the present state only. So in this one it was dependent on present state and dn, but in this it's only dependent on the present state. So I'm going to begin the process, and then I'm going to type case present state is when st0 is set, then d out should be set as 0, when st1 d out should be set as 0, when st2 I'm going to be setting it as d out equals 0, when st3 d out should be set as 1, when others and others, d out should be set as 0, and then I'm going to end case and end this process. So what I've done in this is that I've declared a process named next state decoder that is sensitive to changes in the present state here, and I'm going to begin the process. The case present state is a statement which checks the current state, which is our current state is the next, if it's our present state, it checks the present state and defines the logic for updating the output d out based on the current state. So based on whatever current present state we have, our d output is going to be updated. When st0, it is going to be 0 d out. st1 d out is going to be 0. st2 d out is going to be 0. st3 is it's going to be 1. So inside each when block, there is a logic for setting the output d out based on current state. The when others block in the end is a catch-all for any states which are not explicitly handled. Similarly here, if there is no state which is not handled, if there is a state which is not handled, that is catched in this others block. So we have implemented the next state decoder. Next is I have to end the program. So for this I will do end behavioral architecture. So this is the code for uh, the Murray state machine, and we will run it now and we will check if there is any errors. Alright, I have done some minor adjusts in this. I'm gonna, yeah, it's running correctly, so I will check the behavioral syntax, and yeah, the behavioral syntax is checked. So now I will be simulating the behavioral model. So yeah, our model has come, the sequence detector 101 using Murray state machine. So I will zoom out. Yeah, you've got it. So this is the model for Murray state machine. So you can click anywhere and you can verify the Murray state machine tables. And yeah, hope you guys enjoy.